Good morning, friends. In the previous lecture we have discussed about principle of operation of switched reluctance motor. Now here I am discussing about how torque is produced in switched reluctance motor. The torque produced in switched reluctance motor is given by equation half I square dl by d theta, where I is the instantaneous value of exciting current in the stator phase winding and L is the self-inductance of the stator phase winding. Here we can see that torque produced is directly proportional to I square. It means that torque is independent of direction of current. But the direction of torque depends on rate of change of self-inductance with respect to rotor position. To illustrate the concept of torque production, refer to figure 9.23a. Here angle theta is taken as 0 and inductance in this position is minimum. Since inductance is minimum, therefore we can say that reluctance is maximum at theta is equals to 0. As rotor is moved clockwise, stator and rotor pole begins to overlap each other, and as a result reluctance decreases and inductance increases linearly. When theta is equals to theta 1, the pole faces overlap and reluctance is seen to be minimum and inductance is maximum. The variation of inductance from minimum to maximum is taken as linear. For rotor movement from theta 1 to theta 2, the reluctance continue to be minimum and therefore inductance is maximum but constant. As rotor is moved beyond theta 2, overlapping of stator and rotor pole faces begins to decrease and as a result reluctance begins to increase and therefore inductance start decreasing. When theta is equals to theta 3, the inductance decreases to minimum value L minimum equal to inductance already obtained for theta is equals to 0. For rotor movement from theta 3 to theta 4 is equals to 180 degree, the inductance remains constant at its minimum value. Beyond theta 4, the inductance begins to increase linearly, which is shown in figure A. 9.24a. The variation of inductance in figure 9.24a is ideal. Here we can see that from when rotor moves from theta is equals to 0 to theta is equals to theta 1, inductance rises linearly. During overlap angle from theta 1 to theta 2, inductance remains constant. Beyond theta 2, inductance begins to decrease till theta 3. Now coming to torque, from equation T, torque is equal to half I square dl by d theta t, we can draw the torque and theta characteristic where we can see that at from theta is equals to 0 to theta is equals to theta 1, when dl by d theta rises linearly, then torque is positive and constant. During overlap angle theta 1 to theta 2, since inductance is constant, it means dl by d theta is equals to 0 and therefore torque produced is also 0. Now beyond theta 2 to theta 3, inductance decreases linearly. Since inductance decreases linearly, that means that dl by d theta is negative and therefore torque produced is also negative. So here we can see in figure 9.24b that during theta 2 to theta 3, torque becomes negative. During from theta 3 to theta 4, inductance is constant. Inductance is constant, it means dl by d theta is equals to 0. It means torque produces also 0. Here I want to tell you one more thing, that average torque is 0 for constant winding current. To obtain only positive value of average torque when phase winding excited only for period dl by d theta is positive and not for when dl by d theta is negative. It means that when dl by d theta is positive, only then we have to supply current in stator winding. When dl by d theta is negative, we don't have to provide current in stator winding. In this way, we will get only positive torque and therefore rotor will rotate. If we want to reverse the direction of rotation, then all the phase winding will be excited during the period dl by d theta is negative and not when dl by d theta is positive. In this way, average negative torque will obtain and which will reverse the direction of rotation of rotor. Thank you.